Okay, welcome. We're going to finish up Chapter 4, Lesson 1, Navigational Elements. I'm going to go through some of the PowerPoints that the Air Force has given us in great detail. Just make sure there's no questions. This will be our final review prior to the test. And let's see, for hybrid students, that will be Monday. I'm sorry, I'm lying. Chapter 4 test is at the end of the quarter, probably around, I think it's week 8. Next week for you guys is Chapter 3 test, as well as on hybrid there'll be Chapter 3 test on Monday. All right, so Chapter 4, Lesson 1, Navigational Elements. Basically we're going through the process of getting from one place to another. We're going through some basics. We also mentioned out of your text that one of the original ways to navigate, of course, is by sight, and that these guys were not even used to cars at the time that the Wright brothers invented planes, and so they were looking at the ground and looking at roads. And actually one of the original ways to navigate, especially at night, is bonfires and bright lights. The 1920s, the government developed a navigational beacon system, which, believe it or not, is still in parts of America operating. It simply sends out a beacon that your plane in your aircraft would dial into, exactly like an AM radio. Do you guys even know what an AM radio is? AM radio, amplitude modulation. But basically you would listen to it and you would tune it in, and when it get very strong, you knew that you were pointing towards the target, the beacon. And then when it get very soft, you know you were going away from the beacon. So it's actually a sound thing versus a indication necessarily in your aircraft. And so that radio navigation beacon system were the original post office planes and aircraft that flew. An altimeter, two-way radios showed up when technology came into the aircraft, but really an altimeter, which is your altitude, and a directional gyroscope, which is their picture on there on the right, the attitude indicator, are still to this day your basic instrument indicators. Yes, sir?
Does the altimeter, does that go off of the air pressure?
Altimeter, yes, it does depend on the barometric pressure, which we actually talked about in one of the previous classes about the flight level. And so you have to manually dial in, of course nowadays some of it's automated, your altimeter setting, which determines your altitude. So when you're going long distances below 18,000 feet, flight level 180, you actually change your altimeter basically a lot of times when you talk to the people on the radio. Then these are a little more complicated, a little longer developed instruments. An airspeed indicator, which measures the pressure differential. You can turn around. The pressure differential, just pull it out and turn around. Pressure differential between a pitot tube, P-I-T-O-T. Every plane has a tube right on the edge of the plane, and actually F-15 is on the side, but usually it's right in the front, and that measures the pressure going in against a static pressure port, or static meaning zero, inside the plane. And the differential on that pressure is your airspeed indicator. Turn and bank indicator, meaning how coordinated your turn is. Again, every plane to this day has all these instruments. A lot of them are digital or on TV screens now. And then the very bottom there, the UHF and the VHF navigational systems. Does anybody here live out near Chino Valley? Okay, does anybody know what Outer Loop Road is? You ever been on Outer Loop Road? Reed Road in Chino Valley? When you're driving on Outer Loop Road or Reed Road to the south side, towards Prescott, has anybody ever seen anything very unusual out there? Looks kind of weird to be sitting in a ranch area.
It's a building with
Give me R5. It looks almost like this picture up here, and it's called a VOR. A Mexican hat, okay? It's got a thing sticking up in the middle of a white thing, and it's basically right on a rancher's property. I don't know exactly how it works out, if the FAA has bought that 1/4 acre or 1/8 acre, or actually they rent it from him. but basically it's a VOR, and it is an intersection in the sky. So when you drive out here on Route Street, you come down to the stoplight, there's an intersection. It's rather important in Prescott because all the kids leaving the Prescott High School and hitting, what's the name of the street? Whipple? What's the name of the street down there the YMCA is on? Whipple, okay. Well, that's a pretty big intersection. It comes through there a lot. Well, that's the same thing in the Outer Loop Road for that Mexican hat or VOR. We're going to talk about that a little later on when we get to navigational maps and stuff like that. Okay, in the 1940s, radar popped up. That was part of the innovation for World War II, to be able to see aircraft coming in without them knowing it. And then in 1967, we have satellites. That is a pretty famous picture of the satellites tracking around the world. Two types of satellites. One's geosynchronous. Does anybody know what that means? Yes, sir?
It means that the orbit always stays above one area on the
Give me Air 5. Did you take my space class?
no, I just
My goodness. Well, that's exactly what I'm teaching next year with space astronomy. We'll go through a lot about GPSs and satellites. When I was in the Pentagon, about a year of my time in the Pentagon, I was in charge of the money for GPSs. And so I know a little bit about that. We talk now about the basic navigation. This is what we've been through the last few days. The quickest way to go from two places on the earth is called a
great circle.
great circle. It's not called a straight line. Matter of fact, somebody, I think, talked about going from even Los Angeles or Phoenix and flying to Hawaii. You don't go due east. You actually fly a great circle route where you actually go a little farther north, where the globe is smaller, and then finally come back down to Hawaii, just like going over the North Pole to get to Russia from here. We talked about that. It's the shortest distance between 2 points on a sphere is a great circle. We also talked about latitude and longitude. One thing I did mention, but I didn't go into a lot of detail, which I will right now, a little more detail, so because you have to know this as far as navigation, is, let's go up here to our... What is, when you have a latitude and longitude, how do we measure latitude and longitude?
Degrees.
Degrees, yes. We do not measure them in miles or statute. Well, we do add miles, but it's a lot different. But it's basically degrees. And if you have the world, okay, what are these right here? Latitudes, exactly. And so the distance between the latitude, when you go up, is exactly the same. Because it's a ladder. It's a rungs of a ladder. What about the, let's see, let me do a different color here. Ups and downs are called, yeah, got it? I need a blue magic marker, are called longitudes. They go from North Pole to South Pole all the way around the Earth. But does everybody see when they go straight up and down that at the north point, the distance between the longitudes are very small. But at the equator, the distance between the longitudes are much wider. So if we're measuring something on the Earth's surface, we always measure distances based on latitudes. Okay? And so we have this as degrees, 60 degrees, and you break up a degree into what?
Minutes, sir.
Minutes, okay? Degrees, minutes. And what is minutes? Seconds, just like a clock, seconds. The way it actually works is 1 degree equals 60 minutes. And then where can I put it? 1 minute equals what?
60 seconds.
60 seconds. So it's sort of like time, but now it's sort of like not, because the way it works is 1 degree of latitude, we said that equals 60 minutes, okay? 1 degree of latitude is equal to a nautical mile. A nautical mile, okay? Nautical mile is 6,000 feet. and we can talk about this, and we'll get into a little more detail when we talk about maps, but how long, and when you're driving down the road and it's a statute mile, how many feet is that?
5,280.
Yeah, 5,280 feet. When you drive down to Phoenix, you say it's 60 miles away, that is a statute mile. That is not what we measure stuff when we fly. When we fly, we measure stuff via nautical miles. Okay, just like a lot of the navigation on the flying came from all the navigation gained from sailing. The Greenwich Mean Time was not designed because of airplanes back in the 1800s. Greenwich Mean Time was designed because of the sailors' needs, okay, the transportation needs. So one nautical mile is, I actually lied. I said 1 nautical mile is 1 degree. 1 degree is actually 60 nautical miles. So 1 nautical mile is 1 minute, okay? And that's equal to about 6,000 feet. It's a little longer, but basically 6,000 feet. Just keep things... 6,080, yeah, but I mean, 6,000 feet is about a nautical mile. So you can see there's a difference from when you say, hey, how far did you guys fly? Well, we flew 60 miles down to Phoenix. What are you talking about? Statute miles on the ground? Or are you talking about nautical miles? And the difference in a statute and a nautical mile is pretty significant. It's what, 800 feet, which is about, 15%. So you got to know what you're talking about, nautical miles or statute miles. And the reason behind it is a nautical mile is based on the degrees and minutes of latitude, which work perfectly. So later on, fourth quarter this year, I'm going to give you nautical maps. I mean, you give maps, and you have to chart this stuff up. And you can sit there and go, gee, there's one degree of latitude. A degree of latitude is equal to 60 nautical miles. And you can measure or estimate stuff real easy. You go, wow, look at there. 1, 2, 3. 3 degrees, 3 times 60 is 180 miles. That's how easy it works. So that's how you measure the distance on a globe, is via latitude, distance, or nautical miles. Okay? How about, let's see, and actually in page 270, it talks about navigational direction. How do you measure the heading that you're going, the direction you're going? How can we do that? When we talk about north, what are we talking about? Where are we pointing to as far as north?
The North Pole.
Great suggestion, but honestly, no. Okay? When you have a compass, it's magnetic. Is the magnetic North Pole the same as the actual North Pole where you sit there and stand on the ground?
No, sir.
Believe it or not, it's not. And there is a difference in the magnetic North Pole and the true North Pole. We'll get into that a little later. But the bottom line is, when you have a compass and you say, I want to go to the magnetic North Pole, that North Pole is controlled by the magma in the middle of the earth, and it varies. It actually wanders around and leaves a little bit. The true North Pole, which is what you're talking about, where you actually stand on the top of the globe, that is a little different. We call everything with a heading. When we say north, what heading is north?
0 degrees.
0 degrees. We do not say that. The North Pole we actually call 360. And if there's any kind of heading, we always use the numbers. So if I'm heading south, what is south?
180.
No, it's not 180. It is 180. Okay? It's just like there's no 18,000 feet flying. It's flight level 180. When you're heading east, what number of degrees is east? 90. No. 090. Okay? So let me educate Colton. What is west then?
270.
Is that correct? No. What is head west?
267.
Okay. And so then back again, what is north?
360.
Error 5, great job. Yes, that's exactly right. So that is all based on the true north, and when you're plotting a vector, you have to have the degrees that you're heading and your speed. Page 273, getting out to charts. We don't really call maps in flying. We really call maps charts. Okay? And the thing is, until you get into reading charts and navigating, and actually they have a pretty good picture there at the bottom of page 273, you don't realize how complicated it is to take a globe and turning it into a flat surface and then navigate. And I was fascinated by this as a kid because, and actually I have it there on the projection. Look at the projection there on the left-hand side, okay? And actually it's this one right, oops, this one right here, okay? This projection here. When they actually took the globe and put it onto a flat piece of paper, it actually was perfect at the equator. So when you take a globe and you actually change it from a globe to a flat piece of paper, it is perfect at the equator. So what does that mean about the size of the land masses at the poles? Yes, sir.
It gets more distorted as you move away from the equator.
Error 5, yes, hugely distorted. And so when I was a kid, because I really didn't like maps, and I'd look at a world map, I go, man, that is a cool island. I want to go check that out. What island is that? Greenland. And how big is it?
Very big.
It is bigger than the continent of South America. Wow. How come we don't go up there and just take it over? That'd be really cool. But is it truly bigger than the continent of South America? No. Greenland is a dinky little island, 1/5 the size of Texas. Okay? You see Texas? You can't even see Texas. I can put my thumb over Texas, and this island up here is 1/5 the size of that. But just like Cadet Rossman said, at the poles, if this is exactly right, at the poles, it is wildly distorted. And I'm telling you, I grew up a long time as a kid going, man, I'm going to go to that cool island. It's big. And it is dinky small compared to what it is. I don't mean to insult anyone from Greenland, but I'm just saying the distortion is kind of crazy how it is distorted. So what about Alaska? Okay, you see Alaska up here? How big is Alaska compared to America?
That's bigger than Texas.
Bigger than Texas, I think the answer is 1/5. Okay, so Alaska is 1/5 the size of the continental United States. But look at this right now. If on this picture, my goodness, it's over half. It's bigger than everything west of the Mississippi. Is Alaska really that big? It's big, don't get me wrong, but it's not that big.
It's twice the size of Texas.
Yeah, twice the size of Texas. So I'm just saying, when you look at a map like that, you kind of need to know what kind of geometric projection it is and exactly how they are. Whether or not it's a conical, you go to page 274, 275, whether or not they have a cylinder projection. A tangent projection is what we were looking at, where it actually is perfect at one spot, like the equator. A secant projection is where you can see it encircles the Earth and is perfect on two lines. And actually, if you go back, you can see over here on this secant projection, it's perfect. The Tropic of Cancer, Tropic of Capricorn is perfect there, but it's bad everywhere else. And so really, when you're talking about maps, maps are kind of complicated. They're just not as simple as you think. For us in America, we're sort of near in the world, we're kind of down close to the equator, and so we're kind of accurate. But if you're living in Alaska, it is not. If you're living in Greenland, it's not. A lot of Russia, right? A lot of Russia is very far north. It's not. You have to know what kind of projection you're at. Look at this projection. That's a projection showing it from the North Pole. Wouldn't the world be kind of different if we projected the south north and the north south and the south up? So, the different types of projection are in page 276. Chess Salters, come here a second, please. One of the hybrid students is online right now, and she's texting me asking me what she's finished. And you're welcome to use my phone and text back. Don't do anything immoral or illegal. How many teachers allow their kids to text on their phone in the middle of class? All righty. So this is most common projection. It's called the Mercator projection. It looks smaller than Greenland. South America looks smaller than Greenland, but in actuality, I was wrong. South America is 8 times the size of Greenland. 8 times. Okay? But we use that in America as the most prominent one because, honestly, it makes America look pretty good size, and also the continents, the major continents are about that size. Okay? Alrighty, that is the end of lesson 1. And I tell you what, let's start again. Let's quickly go through some of the important vocabulary. 263. We need to know what an airway is. We need to know what an attitude indicator is. A great circle, we talked about that. We talked about the quickest way around a sphere is a great circle. We talked about the longitude. Where does the prime meridian go through, guys? Greenwich Mean Time. Greenwich, England, a dinky little, Royal Observatory. One time it was very famous.
I thought it was Greenwich.
Greenwich. You're saying a uneducated American pronunciation of Greenwich. How do you pronounce Prescott? So the proper way to pronounce Greenwich is Greenwich. And true north. The true north goes straight to the North Pole. We talked about headings and tracks, ground speed. Ooh, I didn't cover ground speed. Let me go back to do that here at the very end. Ground speed. I tell you what, let me call that. What page was that on? There you go, 271. We got to go through that. That was good that I did that. 271. I mentioned about the airspeed, miles per hour, nautical miles per hour. If you look at that chart there on the bottom of 271, and this has happened to me, if you're in an airplane traveling 100 miles an hour and there is no air, guess what? Across the ground, you're going 100 miles an hour. But if you have a tailwind of 20, then your ground speed is 100 of your plane plus the tailwind, and that's 120 miles an hour.
Makes you go faster.
Makes you go faster. Converse is true. What if you're traveling in a 100-mile-an-hour plane and maybe you're flying over some mountains, and it could happen. Actually, plane, let's say a Cessna. Let's go you're 70 miles an hour. And you're flying over Prescott, Arizona winds that are having a bad day, and it's 70 miles an hour. And if you're flying into a 70-mile-an-hour headwind and your plane goes 70 miles an hour, how fast are you going?
Go to 0.
Well,
You don't crash.
a complicated question. When I say how fast you're going, your question should be, sir, what kind of airspeed are we talking about? Are we talking about ground speed or indicated in the plane? I'm going 70 miles an hour indicating the plane, but across the ground, I'd be going goose egg 0. So again, when you say, gee, sir, how high have you been flying? Well, that's kind of a complicated question. When I say how fast you've been flying, it's kind of a complicated question, like 5 different airspeeds. We say, gee, sir, how far have you been going? Well, sir, are you talking about statute miles? Or are you talking about nautical miles? You got to be a little specific there. I need you guys to know that. All right, we will stop lesson 1 right now and proceed to lesson 2.